In this video, we're talking about how to find the critical numbers or critical points of a function. And in this particular problem, we've been given the function f of x is equal to x to the 1/3 power minus x to the negative 2/3 power. Now, before we go any further, we need to talk about critical numbers versus critical points. Sometimes you'll see it written both ways. Oftentimes, people use critical numbers to refer to potential critical points. So if you see critical numbers, what it probably means is values of x where the function may change direction, versus critical points where we've confirmed that in fact the function does change direction at that particular point. So when you're finding critical points, there's really two steps to the process. The first step is to identify potential critical points or critical numbers, and then the second step is to test each of those points to verify whether or not in fact they are critical points. In other words, whether the function does in fact change direction from increasing to decreasing or from decreasing to increasing at that point. So the way that you're always going to go about finding critical points is the method that we're going to use in this video. And what you're going to do is you're going to start with the original function f of x. And in order to find critical points, your first step is going to be to take the derivative of this function, which of course we'll call f prime of x. So when we take the derivative, we'll go ahead and say f prime of x is going to be equal to, and then taking the derivative is just about applying the derivative rules that you're going to need based on the kind of function that you have. So in this case, we're going to need to use power rule because we've got power functions. So when we take the derivative of x to the 1/3, remember we bring this exponent down in front here, so we get 1/3 times x, and then we subtract 1 from the exponent. So 1/3 minus 1 gives us negative 2/3. So that's the derivative of x to the 1/3. Now we have to take the derivative of negative x to the negative 2/3. So first of all, we'll keep the minus sign here, and then we'll bring this negative 2/3 exponent down in front. So we'll say times negative 2/3. We'll keep the x, and then we'll say negative 2/3 minus 1, which is going to give us a negative 5/3. So this is going to be our derivative, but we want to go ahead and simplify it because we have a negative which will cancel with this negative. So we're going to get 1/3 x to the negative 2/3 plus 2/3 x to the negative 5/3 for our derivative function. Now, once you have the derivative function, your next step is always going to be to look for values of x that are going to make the derivative function one of two things, either equal to 0 or undefined. So what we want to do is we want to set this function, the derivative function, equal to 0, and then we're going to solve for any values of x that make this equation true where the derivative is equal to 0 or where the derivative is undefined. So we can go ahead and factor the right-hand side here. We can factor out a 1/3. We can also factor out an x to the negative 2/3. So what do we have to multiply by 1/3 x to the negative 2/3 to get 1/3 x to the negative 2/3? Well, of course, just 1. And then we pulled out a 1/3, which is just going to leave us with a positive 2 here. We have to multiply 1/3 by 2 in order to get 2/3. And then what do we have to multiply by x to the negative 2/3 in order to get x to the negative 5/3? Well, that's just x to the negative 1, so we can say x to the negative 1, and now we've got the right-hand side factored. Let's go ahead and rewrite this so we get rid of our negative exponents. We're going to say 0 is equal to, and remember when you have a negative exponent in the numerator, you can go ahead and move the entire term to the denominator in order to make the exponent positive. So this becomes the 1/3 is going to get incorporated into the fraction here. So we're going to have 1/3, and then this x to the negative 2/3 moves to the denominator to become x to the positive 2/3, multiplied by 1 plus, and same thing here, 2 is going to be in the numerator, and x to the negative 1 becomes x to the positive 1 in the denominator. Now, zero theorem tells us that we can set each of these factors equal to 0 individually, because if this value, 1 over 3x to the 2/3, if this value is equal to 0, then the equation is true. If 1 plus 2 over x is equal to 0, then the equation is true. So we can set these equal to 0 individually and say 1 over 3x to the 2/3 equals 0, and 1 plus 2 over x equal to 0, and solve these equations individually. So for this first equation here, 1 over 3x to the 2/3, there's no value here that we can plug in for x that's going to make this equation true. If we plug in x equals 0, if x is equal to 0, then this equation is undefined because we'd have 0 in the denominator. So we're going to go ahead and say x equals 0 makes the derivative function undefined, and therefore that's a potential critical point, because remember, for critical points, we're looking for values of x that make the derivative either undefined or equal to 0. In this case, x equals 0 makes the derivative undefined, so we are interested in that point as a potential critical point. Then we go over here to this equation. Let's go ahead and subtract 2 over x from both sides. That'll give us 1 equals negative 2 over x. Then we'll go ahead and multiply both sides by x, and we'll get x is equal to negative 2. Now, x equals negative 2 is a potential critical point because x equals negative 2 makes the derivative equal to 0. So both of these are potential critical points, but we can't call them actual critical points until we've tested them. Now, before we talk about how to test these critical numbers or these potential critical points in order to verify whether or not they are in fact critical points, let's talk for a second about why we have to set the derivative equal to 0 and look for values of x that make the derivative undefined or that make the derivative 0. Remember that critical points represent values of x where the function changes direction. So the function is increasing on one side of the critical point and then decreasing on the other, or vice versa. So for example here, if this is the graph of our function, point D here, we can see that the function is decreasing to the left of D, right? It's starting here at C and it comes down, it's decreasing on the left side of D. Then when it gets to point D, it starts increasing, it's moving in the positive direction. So we have decreasing and then increasing. So D would be a critical point of this function here. But because there's a corner or a sharp angle here, the derivative of this particular function would be undefined at the point D. And if we only looked for values where the derivative was equal to 0, we would miss point D as a potential critical point. So D here is an example of why we have to look for values of x that make the derivative function undefined. The reason we have to look for values of x that make the derivative function equal to 0 is to identify critical points like b and c here. You can see that b and c are critical points because they represent points where the function changes direction. So if we look at point b, we can see that on the left-hand side of point b, the function is decreasing. It's going down toward b. Then when it hits b, it starts increasing and it's going up in the positive direction. Here at point C, on the left-hand side, the function is increasing towards C, and then once it hits C, it starts decreasing down toward point D. So B and C both represent critical points of this particular function. And at these points, the derivative is equal to 0 because remember, the derivative just represents the slope of the function. Remember that the slope of a horizontal line is 0. So if we look at the tangent line at these points, or the slope of the function at points B and C, the tangent line, or the slope equation here, would be a horizontal line. Same thing here at point B. The tangent line would be horizontal at point B, and therefore the slope of the original function would be 0, which means the derivative would be equal to 0. So at these 2 points here, the derivative f prime of x would be equal to 0. So that's why we set the derivative equal to 0 to solve for potential critical points like b and c. But the reason that we have to test the potential critical points that we find is because we can have critical numbers that don't actually turn into real critical points. For example here, this point A, if the function gets perfectly horizontal here, we'll find a tangent line that is horizontal through this point A, so the derivative will be equal to 0, but the function actually just crosses the tangent line as opposed to changes direction at the tangent line. And so for this function, we would identify point A as a potential critical point, but if we tested it, we would see that the function is decreasing to the left of A and continues decreasing to the right of A, and therefore the function doesn't actually change direction there, so it's not a real critical point. So how do we go about testing the critical numbers that we found to see if they're actual critical points? Well, what we want to do is plot any critical numbers we found on a simple number line. So we'll take a number line like this. And what we want to do is plot these critical numbers left to right. So we have x equals negative 2 and x equals 0. So we'll say negative 2 and 0, like a normal number line. And we want to test values that are in each interval. Notice that the 2 critical numbers break the number line into 3 intervals. Everything to the left of negative 2, everything between -2 and 0, and everything to the right of 0. We need to test each of these three intervals to verify the behavior of the original function on each interval. So we'll go ahead and look at -3, we'll look at -1, and we'll look at +1. Now, the easiest way to test critical numbers is to use the first derivative test. So we're going to plug these values, -3, -1, and 1, into the first derivative. So f prime of x is our first derivative. So in order to test each of these values, we'll plug them into f prime. So we'll go ahead and say f prime of -3, our first test value here, is going to be equal to, and now we just plug this value, -3, into our derivative function. We'll plug it into this equation here because it's simpler. We've gotten rid of our negative exponents. So what we'll get is 1/3 times x to the 2/3. Well, that's the same as saying x squared and then take the third root. Because we've got -3, we're going to take -3 squared, or 9. So this is going to be the third root of 9. Then we're going to multiply that by 1 plus 2/3. Now what's important here is not the actual value of this equation here at -3. What's important is whether or not the result here is positive or negative. So if we look at this, we'd say 1 minus 2/3 is going to be a positive 1/3. This value here is obviously going to be positive because it's all positive numbers involved, which means the value here is positive. And again, we don't care about the actual value, just whether or not it's positive or negative. We'll come back to this in a second, but now let's go ahead and test f prime of -1. So we'll say f prime of -1 is going to be equal to, going back to this equation here and plugging in -1, we're going to get 1/3. -1 squared is a positive 1. Taking the third root of positive 1 is just 1, so we get 1 there, multiplied by 1 plus 2/1. Inside the parentheses here, we've basically got 1 minus 2, which is going to be a -1. We've got a negative value times a positive value out in front, so we're going to get a negative value. Now, if we test our last value, +1, in the first derivative, we're going to get f prime of +1. That's going to be equal to 1/3 times 1 to the 2/3, which is just 1, times 1 plus 2/1. 2/1 is 2, plus 1 is 3. We've got a positive value inside the parentheses and a positive value outside the parentheses. A positive times a positive is a positive. So what we want to indicate then is that our test value of -3 gives a positive result in this interval. Our test value of -1 gives a negative result in this interval. And our test value of +1 gives a positive result in this interval, which tells us, based on the signs that we get here, that the original function is increasing in this interval because the derivative is positive, that it's decreasing in this interval because the derivative is negative, and that it's increasing in this interval because the derivative is positive again. And now what you've got is a picture that makes it real obvious that if the function is increasing to the left of -2 and then decreasing to the right of -2, then x equals -2 has to be a critical point because the original function changes direction there from increasing to decreasing. Therefore, x equals -2 does represent a critical point of the function, and in fact, it's a local maximum because in the same way that point C here, the function is increasing to the left and decreasing to the right, and here we have increasing to the left and decreasing to the right, you can see that in the area of C, C is the highest point, so it's a local maximum. Well, x equals -2 in the same way has to represent a local maximum. Also, we can say x equals 0 represents a local minimum because the function decreases to the left of x equals 0 and increases to the right of x equals 0. So this is sort of the bottom of this dip here, and therefore the original function has a critical point at x equals 0 that represents a local minimum. So now at this point, we think we found a local maximum at x equals -2 and a local minimum at x equals 0. The last thing you have to be aware of when it comes to critical points is the graph of the original function. If you can, you should always try to graph the original function. Most of the time, this first derivative test method is going to work. For you to find critical points this way, test them to verify that the function does in fact change direction, and then draw a conclusion about local maxima and local minima. But sometimes critical numbers that appear to be critical points are actually going to lie outside of the domain of the original function, in which case they aren't in fact critical points. So again, the vast majority of the time, this is going to work. But in the case of this particular function, the given function f of x, if we graph it, here's what we see. we see that we have a function with a vertical asymptote at x equals 0, and the function is only defined for positive values of x, and it's always increasing. You can see that as we move left to right, the function is always increasing, and it's only defined to the right of x equals 0 for positive x values. So this x equals -2 value doesn't exist in the domain of the function, nor does x equals 0. X equals 0 is not part of the domain of the function because for this particular function, the domain of x is only positive values of x. Therefore, what we would say is that there are actually no critical points because there's nowhere in the domain of the function where the function changes from increasing to decreasing or from decreasing to increasing. In this function's domain, it's always increasing, and that should make sense according to our chart here because what we can see is that the domain of the function is everything to the right of x equals 0. So if we sort of cut this off right here, we can see that this chart tells us that the function is increasing to the right of x equals 0. What's irrelevant is everything to the left here. So again, most of the time this method will work where you find critical points and then use this first derivative test to verify whether or not the function changes direction. But the last thing you should always do is graph the function to verify, in fact, that what you think are critical points do exist inside the domain of the function. If they're not in the domain of the function, then they become irrelevant. Otherwise, if they are in the domain, then you verify that they are in fact critical points and therefore do represent local maxima or minima. So that's how you find the critical numbers of a function and test them to see whether or not they are in fact critical points of the function.